The Alexkor zero-back EMF coils. Alex in Russia, who has shared several of his motionless pulse charging systems for batteries, now shares his design, which does not appear to have any back EMF effect on the primary coil. If that is the case, then any increase in output current draw does not have a corresponding increase in the current flowing through the primary coil. That is completely different to the way in which a conventional transformer operates. The arrangement is somewhat like the transmitter-receiver arrangement of Don Smith, and while it looks to be a simple arrangement, it isn't. Alex draws his coil configuration like this. Here, his chosen form of construction is a frame of 12 lengths of 20 mm diameter plastic pipes, 4 at the top, 4 at the bottom and 4 verticals. Each pipe is filled with ferrite powder and there is an output coil wound on each of the 4 vertical pipes. Suspended in the center is the primary coil, which is 15 mm in diameter. All 5 coils are wound using 0.5 mm diameter enameled copper wire, SWG25 or AWG number 24. While Alex's drawing shows a single strand of wire, the actual arrangement for the 4 output coils is that they are wound as a single layer bifilar coil. For this, the output coils are wound with 2 strands of wire side by side, in a single layer along the length of the plastic pipe. Then, the start of one wire is connected to the end of the other wire. As the coils are filled with ferrite, they can operate at high frequency, when the 15 mm primary coil is fed with either direct current pulses or an alternating current sine wave. Each output coil can provide a separate output, or the output coils can be connected in series to give a higher voltage or connected in parallel to give a higher output current. Alex also shows how ferrite toroids can be used, even with 220 volt mains, to give back EMF-free transformer operation. If the input frequency is as low as the mains, then the toroids may be iron dust types, or they can be constructed from iron shims in the same way that ordinary mains transformers are constructed. However, please understand clearly that the current flowing through any coil connected across a high voltage source such as 110 volts or 220 volts and using any of the following configurations, is limited by the impedance of the coil itself. Impedance is effectively AC resistance at the frequency of the alternating current voltage supply. If the coil impedance is low, then the current flowing through the coil will be high, and since the power dissipated by the current flow is voltage times current, the power dissipation with increased current goes up very quickly when the voltage level is as high as 220 volts. The power dissipation is in the form of heat, which means that with excessive power dissipation, the wire in the coil is liable to melt or burn out in an impressive flash of flame, smoke and blackened wire. Consequently, the coil winding needs to have many turns and the wire diameter needs to be sufficient to carry the current flow. The wire table on page 1 of the appendix shows the current which can be carried by each size of wire when wound into a coil. If there is no back EMF effect with the following configurations, then the current in the primary winding connected across the mains will not be affected by the other coils, so remember that when preparing the primary coil. The first arrangement uses 3 toroids to give 4 separate outputs. The amount of current which can be drawn from any secondary depends on the amount of magnetic flux which can be carried by the magnetic core or cores between the primary coil and that particular secondary coil. Obviously, the output current draw will also be limited by the current carrying capacity of the wire used in the secondary coil. If that level of current is exceeded for any length of time, then the insulation of the wire will fail, turns will short circuit together, the coil impedance will drop, the current increase further and the coil will burn out, so common sense is called for. Here, the primary coil 1 is wound on a toroid which is horizontal in the picture above, and the secondary coils 2 are wound on toroids which are shown as vertical in the drawing. The important point here is that the toroids with the secondary coils touch the primary coil toroid at right angles, that is, at 90 degrees. For convenience of winding the coils, any toroid can be assembled from 2 half toroids, which allows the coil to be wound separately. And when completed, slid onto one of the C-shaped half toroids before the 2 halves are placed together to form the complete toroid. The second arrangement 3 toroids. The third arrangement uses 4 toroids, in a more powerful arrangement where the magnetic flux carrying capacity of the transformer is doubled as the cross-sectional area of the toroids inside each coil is doubled. This is a more difficult arrangement to construct, and if the coils are to be wound on a separate coil winder, then the toroids each need to be made from 1/2 toroid plus 2/4 toroids so that the coils can be slipped onto 2 separate quarter toroid sections which are curving in opposite directions, unless of course, the inside diameter of the coils is a good deal larger than the toroid cross-section, which reduces the number of turns for any given length of coil wire. If these simple transformer arrangements operate as back EMF-free devices as claimed, then the current draw from any, or all, of the secondary windings does not have any effect on the current flowing through the primary coil. This is quite unlike present-day commercial transformers which are wound symmetrically, which in turn causes the current draw in the secondary coil to force an increased current in the primary winding. Alex http://www. Radiant4u.net also shows another arrangement which uses 7 toroids. He states that this arrangement is also free from the energy-wasting back EMF designs used at present in most commercial items of equipment. He specifies that the intended operating frequency is 50 Hz, which is the frequency of the mains, as the difference between 50 Hz and the 60 Hz used in America is not significant in any way. This frequency suggests that the toroids could readily be made of iron as in commercial transformers. The prototype was wound with 0.5 mm diameter wire and aimed at a power level of 100 watts. The capacitors are high-power oil-filled with capacitances up to 40 microfarad and rated at 450V when using 220V mains input. The tuning is very much like that of the rotoverter shown in Chapter 2. The physical layout is: the central toroid is wound all around its circumference as indicated by the blue color. This winding is fed directly with the input current source, which would normally be from the mains or from a mains transformer, probably at a lower voltage. There are then 12 output coils, 6 shown here in green and 6 shown in red. For best operation, each of these output coils need to be tuned to the central coil, and that needs to be done by altering the capacitor size by experiment to get the best performance from each coil. When properly set up, increasing the current draw from any of the output coils does not increase the power flowing into the central input coil. This contradicts what is normally taught in schools and universities, as they are only familiar with symmetrically wound transformers and motors where increased output current does indeed oppose the input power, causing increased input current and heat waste. The circuit is: the blue coil has the power input at A, and the capacitor in series with each coil is there to get all of the windings to resonate at the same frequency. The items B and C represent the useful load being powered by each coil. Although, obviously, only 2 of the 12 output coils are shown in the circuit diagram above, and there are an additional 5 green and 5 red coils which are not shown in the circuit diagram. It is probably worth remembering that adding a magnet to a toroid or closed-loop core transformer can boost the output, provided that the permanent magnet is not strong enough to saturate the core completely and prevent oscillation of the magnetic flux. This has been shown by Lawrence Tseung, Graham Gunderson and others, and so it might be worthwhile to experiment further with these configurations along the lines shown in the video at www.youtube.com. Watch the easiest version. Alexkor has produced a simplified lens law-free design, using commercial toroids already wound as step-down mains transformers. One supplier is http://www.electro-mpo.ru/card8524.html number sign VSV 7S with transformers of this type on offer. The technique is to remove the plate covering the central opening and connecting the 220 volts and 110 volts windings in series. 2 of these transformers are used, each of them connected with their 220 volts and 110 volts windings wired in series, and then the toroids either placed side by side or alternatively stacked on top of one another with a 1 mm thick sheet of plastic between them. In the configuration where the toroids A and B are placed side by side, a power extraction winding D is wound between them. In the case where the toroids A and B are arranged in a stack with 1 mm plastic sheet between them, the power extraction winding D is wound around the two toroids, enclosing them both. While the winding D is shown as a narrow strip in the diagram, that is only to make the drawing easier to understand, as in reality, the winding D is continued all the way around the whole of the circumference of the toroids, and it can be many layers deep to suit the desired output voltage. Toroid A has a tuning capacitor C1 which is adjusted in value to achieve resonance in that circuit, as that minimizes the current flowing into toroid A from the mains. Toroid B has a capacitor C2 which is adjusted to give the highest output voltage, typically 600 volts, coming from toroid B. The purpose of toroid B is to divert the reverse magnetic flow in toroid A and so, produce an efficient working system. The load L is in theory, a dummy load, but in reality there is no reason why it should not be considered to be an actual working load if that output is convenient to use. The output winding D is free of the Lenz's law effect, and the input current from the mains is not affected in any way when the current draw from coil D is increased, or even short-circuited. Alexkor stresses the fact that as the toroids are supplied already wound, this is actually a very easy design to replicate.